Hi, everyone. In this example, we're going to do direct comparison test on this particular series here. So let's say we're trying to know the convergence and divergence of the sum from 1 to infinity of k cubed over 2k to the fourth minus 1. So let's go ahead and kind of do that, and I'll zoom in so we can have more room. So first, we need to give some names to what we will have to work with. And the first thing I want to name is the terms of my original series. So I'm going to let a of k be the terms of the original series that I'm working with, the k cubed over 2k to the fourth minus 1. Now, again, as mentioned during class, what we're going to choose as the term of the series that we're going to compare is we're going to take the highest term of a of k in the numerator and the highest term of a of k in the denominator and take that quotient of it. So for this particular problem, we are going to let b of k be the quotient of k cubed over 2k to the fourth. So that's going to be our b of k for this problem. Well, before we keep going, we need to determine if the series with b of k in it converges or diverges. So let's go ahead and try to see if that series converges or diverges. So if I were to throw b of k inside of a sum, I can't quite tell right off the bat if the sum from 1 to infinity of k cubed over 2k to the fourth converges or diverges. However, notice I can simplify those terms because I have a k cubed in the numerator and a k to the fourth in the denominator. So that simplifies down to a k in the denominator. Also notice that 2 is not dependent on my index k. That means I can pull that 2 in the denominator out of my series. If I do that, I can simplify my sum to be 1/2 times the sum from 1 to infinity of 1 over k. And now from this, now I can determine from here if I do have a convergence and divergence series because I have a p series, my p is 1, and it is equal to 1. So by p series test, I can say that this series diverges by that p series test. So let's put that down. I know that this series diverges by the p series test. And I know it diverges by the p series test because my particular p here is 1, and p series test says if it's less than or equal to 1, it will diverge. One comment in terms of your justification for diverge. Recall from the previous section that this is the harmonic series. And so because it's a harmonic series and as a well-known divergent series, if you would just say diverges since it's the harmonic series, that would also count as justification as well. So if you just wrote yes as your justification for this particular series overall, that would work as well. So let's go ahead and relate why we need to do step 2. So we show that the series we want to compare with diverges. What that's going to tell us is tells us for step 3 what inequality we need to work with. In this case, this tells us that I need to show that the terms of the series that I'm comparing with must be smaller than the terms of my given series for all values of k. So that tells us for step 3, I need to show that b of k is always smaller than a of k. So let's try to do that. And first, since we need to show these for all of for all of k, we need to kind of figure out where to begin here. So I'm going to do some scratch work. And I'm going to try to determine kind of how to go from there. So I know that what I want is I want to show that b of k is less than or equal to a of k. So that's what I want to show. I want to show yes. Okay, well, I know b of k is k cubed divided by 2k to the fourth. And I know a of k is k cubed divided by 2k to the fourth minus 1. Okay. Well, right now it's not obvious to me where to begin for my actual work to show that inequality is true. But it just kind of gives me something that I can kind of play with. Notice that I have k cubed on both sides of that of that inequality. Which means if I were to divide both sides by k cubed, I could get rid of that k cubed and have only the terms of my denominator. So let's go ahead and write that down. I would get 1 over 2k to the fourth is less than or equal to 1 over 2k to the fourth minus 1. Well, still not quite obvious to me if that is obviously true as a starting point. So I'm going to move those terms to the numerator. And if you move those terms to numerator, you get 2k to the fourth minus 1 is less than or equal to 2k to the fourth. Okay, well now I have a big hint. Notice I have the same expression on two different sides of this inequality. So if I were to subtract both sides by 2k to the fourth, I'll be left with a -1 on the left-hand side, but I'll be left with a 0 on the right-hand side. So I'm left with -1 is less than or equal to 0. And this is definitely obviously true inequality. -1 is definitely smaller than 0, so that means it's definitely less than or equal to 0. So that means for that scratch work, we have a starting point in terms of how to do our actual work. So let's go ahead and do that. So again, from class, the way we do it is we essentially take our scratch work and we read backwards up to actually justify that our inequality is true. So again, we start from an inequality that I know is obviously true. In this case, from our scratch work, I reached an inequality that was obviously true, and now it's that -1 is less than or equal to 0. So we get to use that. And now let's go backwards. We said from our scratch work, if that was true, then this must be true. Now I get to go backwards and say that 2k to the fourth minus 1 is less than or equal to 2k to the fourth. Well, that means if this is true, if I were to take the reciprocals on both sides of that inequality, I should get this again. So that must mean that 1 over 2k to the fourth must be less than or equal to 1 over 2k to the fourth minus 1. Well, let's go back to our scratch work. If this is true, that must mean the next line above in our scratch work has to be true. So I can multiply both sides by k cubed. And since k cubed is always positive, I am guaranteed that I do not change the order of my inequality here. And now I have it. I have that a of k is on the right-hand side, b of k is on the left-hand side. So I showed my work. I showed my work that b of k is less than or equal to a of k for all values of k. So zooming out and kind of going through all of our work, because my series I'm comparing with diverges, and because I just showed that b of k is always smaller than a of k, well, since the series with b of k diverges, I only have one option for the series with a of k, and that is that series diverges as well. So I get to state that as my conclusion. So for my overall final conclusion, I get to say overall that my original series with the terms a of k, I now know that series diverges, and I know it diverges by the direct comparison test. So a comment here about my conclusion. Notice that because I defined a of k previously in my work, I've given those terms a name, and so now I can call it that name. That's why in my conclusion, you see me write down the sum from 1 to infinity of a of k. I did that because I already called a of k, k cubed over 2k to the fourth minus 1. So I get to use that as its name in my conclusion. All right, let's try this with another one that's a little bit more complicated. So we tried this series out using the integral test back in the previous section. And we showed in this example, when we did this in 10.4, we already know that this series is going to diverge. So keep that in mind, that in section 10.4, we already showed that this series diverges. What we want to show is how we can use the direct comparison test in order to determine if this series diverges as well. So let's kind of go through our motions of direct comparison test. Now again, I need to define the terms of the series that I'm given, which in this case is that natural log of k over k. But here we need to be a little bit more careful about how we're going to choose b of k, because our initial strategy of choosing the highest term in the numerator and the highest term in the denominator is not really going to cut it here. However, I can choose that k in the denominator. That part's fine. But that natural log of k, I don't really have a highest term I can choose here. So with that, let's kind of go and graph the natural log function to kind of see what the numerator should be. So here's a rough sketch of what the natural log function looks like. And one key thing that I'm going to exploit, and I'm going to go back to my series. Notice that this series begins at 3. It doesn't begin at 1 here. So I'm going to use that to kind of help me out to determine what my numerator should be. And the reason why I'm bringing that up is because my numerator or my series begins at 3 and not at 1, I could kind of use that to kind of help me out here. And here's how I get to use that. So I know E is 2.7 whatever here. And I know that at the point E, if I were to plug that in, that should be a 1. And that should be x equals E. So my apologies there. I know that if I plug an E to the natural log function, I will get the output of 1, because the natural log and the E will cancel each other out. Okay, well, since my series begins at 3, that means what I'm really looking at is anything bigger than 3. So that kind of hints, okay, for the natural log function, I know it's bigger than 1 as long as x is bigger than E. So because I know it's bigger than 1, I kind of get to use that to help me out quite a bit. And as to choose what will be going in my numerator, because I have this observation that the natural log of x is bigger than 1 when x is bigger than E, that kind of hints that my numerator for the terms of the series I'm going to compare with should be 1. So my b of k will be 1 over k. Now, the series that we're comparing with, now this is the harmonic series. And we already know that this series is going to diverge from the previous example. So the series that we're comparing with, the 1 over k, sum from 1 to infinity, I already know that this series diverges. And as mentioned in the previous example, you can either say by the p-series test, since your p is 1, less than or equal to 1, or you can also say that it also diverges, that series needs to begin at 3, since it's the harmonic series. So you can say either or here. And again, I can only do that if it's a p-series for p is 1. If it's any other power, I cannot say that. I have to use p-series test no matter what. All right. So let's go ahead and split this a bit. So again, with my scratch work, which I'll abbreviate as XW, because my series that I'm comparing with diverges, I want to show that for all of k, I want to show that 1 over k is less than or equal to the natural log of k over k. Okay. Well, in order for that to be true, one has to be less than or equal to natural log of k. Well, let's look at yes. That needs to be a lot greater than or equal to, so my apologies. Actually, no, that's fine. So let's go back to our observation. From that observation, the natural log function is always bigger than 1 when x is always bigger than e. Well, in my scratch work, because my series begins at 3, that means all values of k that I'm looking at must be bigger than 3. Well, e is 2.78, whatever decimal after that. So that means k is definitely bigger than e, which means based on that observation, I have this as my starting point. I have a point where I know this guy is true. So let's go ahead and do that and go backwards for my actual work to show the inequality is true. If I were to go back and show that an actual inequality is true, what I'm going to get is the following. I'm going to start from 1 less than or equal to the natural log of k. Now, if this is true, that must mean if I divide both sides by positive k, that must also be true. So I have my desired inequality that the terms of the series I'm comparing with are always smaller than the terms of the series that I'm given. And because I concluded that my comparison series diverges, I get to say, again with the direct comparison test, that your series must also diverge via the direct comparison test. So I get to say that again as my conclusion. So I get to say that the series sum from k equals 3 to infinity, a of k, where again, I defined a of k earlier. I already know what a of k is because I gave it a name. I now know this diverges, and I know it diverges by the direct comparison test. All right. And so with direct comparison tests, I have one big comment to make about this. Now, if you have that your series that you're comparing with converges, but you accidentally showed the utter inequality, you essentially showed that a of k is less than or equal to b of k, you cannot apply the direct comparison test. And the reason why I cannot use that is if I showed the opposite inequality that I wanted to show, well, since everything is positive, I'll get a of k is less than or equal to the sum of b of k, because since everything is positive, if a of k is smaller than b of k for all values of k, if I were to infinitely sum those up, it would still be true. But since the series with b of k converges, it goes to some value x. That's not quite helpful for me to determine if the sum for a of k converges. Likewise, if I have that my comparison series diverges, but I showed the opposite inequality that I wanted to show, I also cannot apply the direct comparison test. So this is the double-edged sword of this particular test, is that if I have convergence or divergence for my comparison series, I'm forced to show a very specific inequality. And if I cannot show that, I cannot apply this test. So we're going to learn of another comparison test that get us around this issue in a nutshell. But before we go into our new comparison test, let's go ahead and see what would happen when direct comparison test fails. So let's say I gave you this particular series here. And let's say that I was adamant on using the direct comparison test to work with this particular series. So let's go for our motions of direct comparison test. So I would define A of k to be the terms of the original series. So in this particular sum, that would be A of k equals 1 over 2 to the k power minus 1. Now for B of k, again, I choose the highest term in the numerator and the highest term in the denominator for my B of k, which in this case will give me 1 over 2 to the k power. If I were to throw that in a sum and check convergence or divergence of that, notice that if after some manipulation, 1 over 2 to the k, well, that's the same as 1/2 all of that to the kth power. So that's a geometric series. Not only that, my common ratio is 1/2, which is smaller than 1. So this series actually converges by the geometric series test. And I know it converges by the geometric series test because my common ratio is 1/2. And I know that that 1/2 is definitely less than 1. Well, if I were to show that my original series with A of k converges, and I was adamant on using direct comparison tests, I would have to show that A of k is less than or equal to B of k. I'm forced to show that now. Well, if I were to do that, again, let's do our scratch work on the side here. That means I'll have to show 1 over 2k minus 1 is less than or equal to 1 over 2 to the k. Okay, it's not obvious if that's true or not, so let's do some manipulation here to see where we can go. And after doing some of our manipulation, you would notice very quickly that we would have a problem if we try to use direct comparison tests. Because notice that after that, I immediately got to 0 is less than or equal to -1. But that's not a true inequality. That's not true. What that tells us is that if I were to try direct comparison test on this series, it's not going to work. So that's sort of why we need to have another comparison test to help us out here. And that provides us to our new type of comparison test. And this comparison test is called the limit comparison test. So let's go through kind of how this test is stated to understand what it says. So suppose you have two series here, one with A of k and the other with B of k. They both have positive terms just like with the direct comparison test. But let's say I took the limit of the ratio of the terms of my given series and the terms of my comparison series, and let's say I got some number L. So let's go through kind of the cases of what we can state from this test. If I know that that limit is a positive finite number, then that means both series must share the same fates. What I mean by that is either both series converge or both series must diverge. And the way that's powerful is the following. Let's say that if I work with my comparison series, I already know that if this series converges or diverges. So what condition 1 is saying here in the limit comparison test is, if I know one series converges or diverges, usually our comparison series, and I get that this limit that I have above here is positive and finite, well, limit comparison test says, well, since both series must share the same fate, if I know the convergence and divergence of one of those series, I must also know the convergence and divergence of the other series. So that's how the limit comparison test is used. I still set up like I would normally, and I would then take the limit instead of showing that inequality. And if that limit gives me some positive finite number, I don't really care what that limit is. All I care about is that it is positive and finite. then because I know that my comparison series converges or diverges, I also know that my given series converges or diverges. Okay, so let's try that again with that series we had before, but this time let's try the limit comparison test instead of the direct comparison test. And when you use limit comparison tests, the first two steps are are essentially the same as with direct comparison tests. So I went ahead and copied down those first two steps from that previous work. I went ahead to find A of k and B of k using the same idea that we did before, where I have A of k be the terms of my given series, and B of k be the terms of the series I'm comparing with by choosing the highest term in the numerator and denominator. I also have to know something about the series I'm comparing with, and by the geometric series test, I know that that series would have to converge. Okay. Well, now, what's going to be different is now instead of doing an inequality, now I am required to take a limit here. So I am required now to take the limit as k goes to infinity of A of k over B of k. Now, my advice here when you work with this limit is usually best to think of it not as a limit of a quotient, but as a limit of a product. So I would advise to separate the numerator and denominator, and instead of thinking of it like a limit of a product of a quotient, you're thinking about it as the limit of a product. So I'm thinking about it as I'm taking the limit as k goes to infinity of A of k times the reciprocal of B of k. And if I were to go ahead and write down A of k and the reciprocal of B of k and take the quotient of that, I would have 2 to the k power times 2 to the k power minus 1. Now, with this, one way that you can take this limit is you can use L'Hopital's rule. And that's because if you were to take the limit of the numerator and denominator separately, you would get an indeterminate form of infinity over infinity. So let's apply L'Hopital's rule here to see what we get. Now recall that for the derivative of a general exponential, like with e to the x, I would copy the original function as well. However, because the base is 2 and not e, to complete that derivative, I would have to take the natural log of whatever that base is. So my derivative of 2 to the k power will be itself 2 to the k power multiplied by the natural log of 2. And notice I get that same expression in the denominator as well. But you can quickly see that, hey, I have the same term in the numerator and denominator. Those two terms cancel. That would give me the limit of the constant 1. And I would get that the limit, or my L, is equal to 1. So before I write our conclusion, let's summarize kind of how to interpret our work. So I have the series that I'm comparing with, the 1 over 2 to the k, proving that in a sum. I know that the series with B of k in it converges by geometric series test. I took the limit as k goes to infinity of A of k divided by B of k, and I got that limit was a positive finite number. Limit comparison test tells me both series must now share the same fate. Both of them have to converge, or both of them have to diverge now. And because I know one of the series converges, well, I have no other option for the given series. It must also converge. So let's state that down. So since I know that my L is equal to 1, and I know that L is positive and finite, now I have to state this because This is my giveaway that says, yep, I can use limit comparison tests. So yes part I do need to state. And because I know that the series with BFK converges, because I showed that work above, then I have no other option for the given series. My given series with the terms of A of K that has to also converge. And I know that guy converges by the limit comparison test. And now there's the other comparison test. I will go ahead and mention that out of the two comparison tests, there's a very good shot you're probably going to use limit comparison test a whole lot more than direct comparison tests. And the reason why is instead of having to use an inequality, you're required to take the limit, which means that all of your tools from Calculus 1 are now fair game. All right, so let's go ahead and try this with another example to kind of iron this new test out. So let's try to do the limit comparison test on this particular series. So let's go for our motions here. I'm going to let A of K be the terms of my original series, that 2k squared plus 3 to the k power over the square root of 5 plus k to the fifth. Now, typically, we'd use the highest power in our numerator and our denominator. I have that k squared in the numerator. And my highest power in the denominator is that k to the fifth, but notice it's inside of a square root. So because it is inside of a square root, when I incorporate that into my BFK, I can't just write down k to the fifth because that k to the fifth was inside of a square root. So that means my highest power in the denominator was actually k to the 5 halves. So my BFK was actually k squared over k to the 5 halves. Now, one thing that's also different compared to the direct comparison test, I highly encourage you to simplify your BFK as much as you can before we keep on going. So in this case, I'm going to go ahead and simplify BFK to 1 over k to the 1 half. Also, another thing to keep in mind, notice I ignored that coefficient of 2. For the limit comparison test, I don't really care about the coefficients. And that's because I'm required to take the limit, and I don't care what that limit is. All I care about is, do I get a positive finite number at the end? So if you want to keep that 2 when you do your setup, that's perfectly fine. But for limit comparison tests, that is not required. Now, I also need to know something about the sum with BFK. And I can quickly tell by p-series tests that this series will diverge. That's because my exponent is 1 half, and 1 half is less than or equal to 1. So I know that this guy diverges, and I know it diverges by the p-series test. I know it diverges by the p-series test. Since I know my p is 1 half, which is less than or equal to 1. Now let's try limit comparison test and have this L be the limit as k goes to infinity of A of k over B of k. Again, it's better if you think about it like a product instead of a quotient. So when you work with this, think about it more as the limit as k goes to infinity of A of k times the reciprocal of B of k. If you do that, let's see what we get. We have the limit as k goes to infinity. I have my A of k terms that I could write down right now at 2k squared plus 3k times the square root of 5 plus k to the fifth. Well, since b of k is 1 over k to the 1/2 power, then its reciprocal would just be k to the 1/2. So when I multiply this out, what I am going to get is I get to distribute that k to the 1/2 power out, which will give me 2k to the 5/2 plus 3k to the 3/2 in the numerator, leaving my denominator alone. Now, in terms of taking that limit, notice that the highest power in the numerator is k to the 5/2. My highest power in the denominator is k fifth, but that is also inside of a square root. So that means my highest power in the denominator is also k to the 5/2. Because the highest powers are equal, I get to read off their leading coefficients. Now notice I put the square root of 1 in the denominator, and that's because I'm emphasizing that the coefficient associated with that k to the fifth was inside of a square root. So in general, if you have another coefficient, that coefficient will be underneath that power. But in the end, I get 2 is my L. So let's go ahead and summarize here in our conclusion. So I have that my L is 2, and I know that that L is positive and finite. That means by limit comparison test, I know now that both series have to converge or diverge. However, I also know that the series that I'm comparing with, I already know from step 2 that the series diverges. So putting all that together, there's only one option for the given series, and that is the y series must also diverge by limit comparison tests. Righty. And with that, that is our entire section on the comparison tests. Let me know if you have any questions, and have a great day.